go. Oh.
Okay, yeah. Thanks, Chiara. You always remember that. I always forget. So this week we welcome Dr. Tommy Thompson. So he is works a lecturer at King's University. He did his bachelor's in computer science at the University of Strathclyde, had a brief hiatus across the country to Edinburgh for his MSc in artificial intelligence, and then back to Strathclyde for computer science PhD. He has 15 years experience in artificial intelligence research in games, and has his own company, AI in Games, and he educates developers and students on how to best to utilize AI in their games. And that is what his talk today is going to focus on, I think. So I'll pass it over to you, Tommy.
Great. Thank you very much. That was a very nice introduction. What to do is to blow me up, because I'm going to jump. And so blow me up in your Zoom, because then I'm going to jump around in different screens and what have you. Okay, so hang on. I'm going to restart the clock so I know my time. Okay, thank you very much for having me. This is quite an exciting time, certainly. And also thank you very much for the introduction. It's always weird to hear your history read back to you, but here we go. So this talk, I'm going to take my headphones off briefly. This talk is essentially a very kind of high-level overview of the state of artificial intelligence in the context of the video games industry, which is something that I am personally very invested in, both in terms of my business side, but also my research career over the years, and also in my teaching. So as just briefly explained there, I run a company called AI in Games, and what I do, this is operated since 2017, and what I do is I support companies big and small in understanding how AI technology, artificial intelligence can be worked within the context of video games, and I revolve really around three pillars. So I do research consultancy, identifying like interesting opportunities and potential technologies for building new tools or systems within games, working as part of a development team, either on a hands-on basis as a programmer or more periodically as like a design consultant. And I communicate work happening within studios to customers and stakeholders and what have you. And in the past couple of years, I've been quite busy with this. More recently, I just finished working as a consultant for Intel Gaming. I've got an ongoing series of projects with Ubisoft at the moment. I'm currently design consultant for 2 different video games at present, one of which is Deathground, which you can see on the right-hand side there, which is a dinosaur survival horror game, which just got kickstarted. And in amongst all this, I also try and make my own games when I can. I work part-time as a lecturer at the Department of Informatics at King's College here in London. And more recently, this is actually something that only just came through, is I am now an advisor to the Game Developers Conference in San Francisco, helping to organize the AI Summit starting next year, which is quite a nice position to be in as someone who actually often talks and is often an advocate for AI in the industry. But the thing is that all of this is actually emerged from my career as a YouTuber, which is a sentence that I still find really difficult to say to this day. So about 6 years ago, I started making YouTube videos about AI in the context of video games, and it was a teaching tool. So I've worked at the University of Derby at that time, and I was teaching a game AI class, and I thought it would be great to find a way to bring the students' enthusiasm for games and my enthusiasm for AI in a way that's more palatable. And YouTube videos, I thought, I had no idea what I was doing, and I then went off and made a whole bunch of them. Since these are some of the videos I made last year, judging by it, this slide's out of date. So we had things like Horizon Zero Dawn, looking at GoldenEye, which is older than I think most of the people in this room. The most recent entries of Hitman, Halo Wars 2, but also actually going to visit the studio at Rare for an insight into the Sea of Thieves series. And then this year I've done games such as The Last of Us, Watch Dogs 2, City Skylines, and actually got to do more insider work with Ubisoft on the Division 2. And very soon there's going to be like a feature-length documentary about Watch Dogs Legion, which just came out like 3 weeks ago. But I also look at academic research, given I have published in this space and I know this community quite well. And so I like to talk about interesting research opportunities that are emerging in this space that aren't really palatable yet in the context of the industry. But I think, oh, this is really cool. People should know about this. And sometimes I just write video essays about the state of the industry. And the kind of weird thing is that it's now got to a point where it's modestly successful. In the last year or so, we actually broke 100,000 subscribers on the channel earlier this year. It's about to break 150,000, I think, probably by the end of the year, which is really exciting. But the channel's also got about 8 million lifetime views now, and it's appeared in a variety of different kind of gaming journalism, which is really cool. But it's always been an aspiration of mine for it to be an educational resource for students, that if you're keen to learn more about games and AI, you can learn a lot from watching it. And you can use it as an academic, you can use it as a base resource for a class, but I also wanted it to be accessible to a wider audience. So if you don't have that scholarly inclination, you can watch it and go, oh, that was cool, I learned something, and then you go off and watch the next thing. So let's talk about AI, and then very much in the context of games. I'm going to start by kind of looking at what has been the state of the industry over the last 20, 30 years. And when we talk about AI, I always like to put this slide in. What we really mean is we're talking about a software system or an agent that can make intelligent decisions of its own accord. And it doesn't require any intervention from the human. So it's an autonomous system, but it's also a rational system. It makes the best possible decision it can in the situation that it finds itself in. And this is pretty much textbook staple of what AI is. But then specifically, we're going to start talking about how different methodologies exist in this space, but also we'll talk a bit about machine learning later on, given that's the big thing everyone's talking about these days, and why it hasn't been used in games all that much in the last, and really until the last 5 to 10 years. So with that in mind, come on, slide. Right. Let's start looking at how AI has historically been used in the game industry. It's an interesting long-running discipline, and how it's used is rather interesting now once you get past the obvious. And it's also a very interesting and unique space for AI applications in the context of really any sort of interactive media presents a very unique space for AI, and we'll get to that in a second. But historically, when we think of AI in video games, we think of bad guys. We think of stuff that's to be beaten up, stuff to be shot, stuff to be defeated. And that's also because games come from a very power-driven dynamic, often these zero-sum environments where you have to eliminate a whole bunch of enemy opponents in order to win. So they needed to find ways for this to become increasingly more complicated. Now, I'm showing Space Invaders here, not that there's any AI in this. This is a really simple program, but historically, there wasn't a lot of AI in this space at that time, given the problem spaces weren't overly complicated and the machines that they're being deployed on are not that powerful. So you couldn't really deploy any sort of really intelligent systems at this stage in order to yield anything of any value. But there's an interesting transition that happened in the 1990s, particularly as we move into 3 dimensions. And screenshot here is from Doom back in 1993. And there's a 5 and 3, 5. Oh no. Anyway, and I'm now old. And what's happening as we moved into 3-dimensional space is that there's a lot of interesting problems that are beginning to emerge that are much more complicated than they were in 2D. And so first of all, there's navigation. How do we make sure that a character is able to move in 3-dimensional space in a way that is effective and optimal, but also respects the topography of the terrain? You have sensory information. So can a character see or even hear you, particularly as these games are achieving a richer level of fidelity? Do we have any ambient behavior? So when a character isn't interacting with the player, does it do something else? And particularly the earlier games such as Doom, actually, they didn't do anything. They actually stood idle and just did a kind of standing idle animation until you shot at them or something else triggered their response. And then also there's the notion of systemic behavior. So what happens when we have different gameplay mechanisms and characters and systems that are just sitting atop one another? And then these allow for really interesting opportunities to emerge that make for fun gameplay experiences, but also keep the player on their toes. And if you fast forward to now, so the screenshot here, this is from Doom Eternal, which is Doom 5 I guess, which was released earlier this year, we're still dealing with the same challenges, but often these challenges are growing at a scale faster than the technology can keep up with it. And it means that AI for games is in a rather unique space where there's a number of tried and tested technologies that enable for a certain amount of behavior that they want to yield. But as the games are becoming larger and more complex, they're having to branch out and diversify and create new technologies, new methods, and begin to research existing tech outside of the games industry to help support that and put it together. But fundamentally, it's still just about creating fun, and building fun opponents, or just fun in the context of a game, is not something that's as easy as creating good opponents or optimal systems. And this is really where I always describe AI in the context of video games as a performance art, because we are more interested in creating a fantasy that exists around the player such that you have a good time and you enjoy yourself. If all of the demons in Doom were this optimal AI, you would appear in an area and they would all just kill you instantly. And you'd be sitting there like, well, this wasn't fun. I didn't enjoy this. So you want to create an opportunity for players to explore and express themselves within these spaces, and then hopefully they're actually enjoying themselves along the way. And so quite often you hear the term game AI used an awful lot in this community, and I'm pretty sure I've already said it, because it's a number of bespoke problems that only exist in games and interactive fiction, but also there's a result of a number of unique technologies that are built only really to cater to games, and often they lift from existing AI applications outside of games, and also that they have to reflect the complex multidisciplinary process that exists, particularly in larger game development. So, for example, the image at the back there, that is from The Last of Us 2. And in this context, when you have characters that are hunting down Ellie, who's the protagonist, you have certain elements of this that are the responsibility of the programmer. They have to build the behavioral system to make sure it works. The designer has to make sure that the different behaviors all sync up in ways that make sense. The animator has to make sure that the character looks like it's behaving and moving in a realistic way. The sound designer has to make sure that it has noise barks so that the character often tells or broadcasts in advance what it's going to do before it does, so the player can learn from it. It's really quite often that great AI in a game is a combination of smart design decisions, effective technology, and a lot of smoke and mirrors to maintain that kind of theatric production. So let's talk about some of the techniques that have been used certainly in the last 20 years, how it's typically employed, and then where the problems are beginning to emerge. So first of all, wind the clock back to 1998, and we're going to look at Half-Life, which is often heralded as one of the most pivotal and influential games in PC gaming, first-person shooter where you play as Gordon Freeman, trying to escape all sorts of hellish monsters that are appearing as a result of a physics experiment gone wrong. And this actually pioneered the use of finite state machines, or finite state automata. Now, this is a concept that already existed outside of video games, but the principle is that the character would exist in a particular state or mode. And then as the events in the world, behavior that's occurring in the world, they could receive input from maybe sensors and what have you, or other game state, other game event logic that would say that it needs to transition from one behavior to another. And so this is actually a really simple approach, but it is markedly effective. And so this is actually footage from the original Half-Life, where these characters are reacting to the world around them. But one of the interesting challenges that they faced during the development of Half-Life was that these characters did not have their own intentions. They did not have their own goals. And so they had to write a bespoke system that sat atop the state machines to say, right, well, this is your goal for this character. They need to find a way to give them some agency that they could then do beyond just purely reacting. Because if all they did was react, then this would actually become really, really apparent down the line. And it's not perfect. We can see, like, we just had a soldier completely ignore me and run past. And then this guy's having a bit of trouble killing me. But over time, like, the technique in this procedure is kind of really refined. To just off the top of my head, some games that actually use this still to some extent, the Batman Arkham series that was on the last generation of consoles and the preceding generation as well. The current reboot of the Doom franchise with Doom in 2016 and Doom Eternal this year, and also The Last of Us with Last of Us 2 coming out this year. All of those games use this particular tool chain, but also they use hierarchical finite state machines as well, where each state is actually a state machine in itself, and it allows for more layered behavior. And then in the early mid-2000s, there was a big push towards trying to enable for them to be more dynamic and to be more goal-driven. And the two big games that came out, there's two big games around the same era. And the first one is Halo 2, which pushed, excuse me, this process known as behavior trees. And what it is a kind of directed structure. It's actually a directed acyclic graph where we always start at the top of this graph, and based on the information in the world, we then follow down this tree to certain decisions where the leaves on this tree are actually going to be bespoke behaviors that we want the character to execute. And so we always start at the roots, and then you have things like selectors, which are essentially conditions. So if the player is close to me, I will take this path in the tree. If not, I will take this path. Or sequences where maybe I have multiple actions I want to put together. So maybe I want to burst into a room and then throw a grenade and then dive behind cover as one kind of continuous action, which is trying to address a larger goal. And so interestingly, like behavior trees are, for all intents and purposes, the standard in the games industry. For people who develop in the likes of the Unreal Engine, there's an entire behavior tree toolchain built right out, it's available for you right out the box, and you can go and use it. It's probably one of the best in the industry. And the vast majority of games actually employ this to some degree or another, to a point that I actually started having to create videos on my YouTube channel about these bespoke topics. I do an AI 101 series, and one of the first episodes was on behavior trees, just so I didn't have to explain what a behavior tree was in every video that it came up in, because I think about half the games that I've covered on the series all use behavior trees. And like I say, still very prominent today. But the other big game that came out in the same era is First Encounter Assault Recon, or Fear, which was developed by Monolith Studios and released in 2005. And it came up with this notion of goal-oriented action planning, or GOAP for short. Now, this is actually a really interesting application, because this is derived from STRIPS, the Stanford Research Institute problem solver, which was developed in the 1970s. And so it was interesting for me because as a PhD student, I was learning about this around the time the game came out, but I was also involved in a planning research group. And so this was something that, as far as planners were concerned, was ancient history, but was blowing up in the game space. And the idea is that you can model actions as having preconditions and effects. And so if a character wants to draw a weapon, then they need to have a weapon in their holster, and they also need to be in a position where it's safe for them to do so. And the effect of then drawing the weapon is they now have the gun. And this is really important if they want to then do actions such as reloading a gun or attacking the player. That gun has to have been drawn in advance. And so sometimes if the character is walking around and they don't have their gun drawn, they will run a plan by running through a planning system and say, I want to attack the player. How do I address this? Well, it's multiple actions that have to be executed in sequence. And what it does is it actually pumps it into a really simple finite state machine where they realize that all actions in the planner are just three behaviors. You could go to a location, you could do an animation, or you could interact with an object in the world. Now, Fear is still held to this day as, if you were to Google right now, top 10 AI in video games, you're going to find Fear in there. And the really depressing part is quite often people still have it in their top 3. And this game is 15 years old. And it's still, like I say, it's still very popular. It's actually still quite a fun game to go back and play to this day. But interestingly as well, it was it led to a small kind of period where it was behavior trees or planning, and people were kind of competing with one another over which of these two systems that they had embraced. And outside of actually creating characters, some of the more interesting things that you can have is directors. These are systems that manipulate and change the game world to keep the excitement focused on you. And it's, while I show you here Alien Isolation, which is probably one of the more famous videos I've ever made on YouTube, the systems that these are were actually originally derived in Left 4 Dead, which came out in 2008. So Left 4 Dead, the idea is that you are one of 4 characters trying to survive a zombie apocalypse. And what I've got here, I'm actually showing you the debug mode of the PC build of the game. And if you own this on PC, you can turn this on. Ask me later or do a quick Google for it. It's actually not hard to do. But what's happening is all these zombies are appearing in the world and they're attacking the player. But the system is actually modeling the perceived stress level that I have. And that stress is calculated based on the distance of the enemies to the point at which I'm killing them, and whether or not I'm having to use melee attacks rather than shooting them. And what happens is it's trying to stress out all of the characters at the same rate. or rough at the same rate. And if they're not feeling stressed, it targets specific players to make them feel more stressed. And it really focuses on getting you to a point of stress, and then it throws everything in the kitchen sink at you, and then you have a moment of respite so you can relax, you can heal up, you can maybe chastise another player because they didn't respect what the other players were doing. And it's actually a finite state machine. Again, it's just, it runs in 3 states. It goes from the peak to the build up and the relax phase, and it just runs this sort of roller coaster of player experience. But the wavelength and frequency of that wave is actually influenced by how you play, because if you do not respect the rules of the system, it actually gets annoyed and begins to attack players, but also speed up the process more aggressively. And directors are now used in pretty much every open world game I can think of. Far Cry, Assassin's Creed, Ghost Recon, The Division, all of these, The Witcher, all of these games of this ilk all use these systems as a means to not only keep the emphasis on the player and keep them engaged, and this is from Assassin's Creed Origins, but also one of the other things it's doing is it's making sure that it only loads characters into the world in proximity of the player, because it can't keep all these characters in memory. It's simply computationally intractable. So they use this as a means to also then actually optimize the game and make it more palatable and easier to run. Quick point I'll raise on constraint programming, and this is actually a procedure where we're trying to satisfy the assignment of variables to values while respecting several constraints. And this is often used in kind of complex scheduling and logic problems. But The Sims is a really good example of this. I wish I actually had some dev footage to show for this, but I don't. Because one of the things they really pioneered in The Sims 4 was the notion that a character can do concurrent behavior. So historically, if a character in The Sims wanted to, for example, watch television while also having a drink of tea or what have you, they would have to do these as 2 distinct behaviors. So it would watch television for a bit, have a cup of tea, and then go back to watching television for a bit. Then what they figured out was this is actually incredibly complicated to manage this in such a way that the characters are in the correct space, that they can hold their cup of tea, put it down somewhere nearby, and be able to watch the television. And so there was a huge amount of investment during The Sims 4 to make this work. And it's one of these tiny inane things that most players won't even recognize, but it's really cool. And I always love this whenever I teach constraint programming and people go, this is completely irrelevant. No one's going to use this. I'm like, it's in The Sims. And then that changes their mind pretty quickly. On top of goal-oriented action planning, there's also hierarchical task network planning. And what this is essentially planning with macros. One of the reasons this became very popular, and 2 of the games that really popularized this were Killzone and Horizon Zero Dawn, both made by Guerrilla Games. One of the reasons this is really popular is that the goal-oriented action planning used in Fear wasn't very good at gluing together good actions together. Essentially, the designers didn't like it because they were at the mercy of the AI system. So if it decided that actions A, C, and E should get put together, but it doesn't think that B and D were good actions, then it'll ignore them. And the designer's sitting there going, well, actually, maybe doing A, B, and C together was a really good behavior, and then action D and E together was a really good behavior. And so this is also derived from outside of the games industry. This is, again, often used in logistics and even in kind of space exploration and stuff like that. And this, like I said, it's really effective in these contexts because designers have a lot more control over the different behaviors these characters do one after the other. And it effectively creates dynamic behavior tree generation. And I think that's one of the reasons people really like it and really gravitate to it. Also, it makes all of these robotic animals in Horizon Zero Dawn really threatening. So if you haven't played this game and if you have a PlayStation or a PC, I'd highly recommend you check it out. Great game. Procedural content generation, which is at a very high level, the notion of algorithmic creation of gameplay assets. So that can be missions, levels, weapons, etc. And this dates back to the 1980s with games such as Elite. And it was often used as a means to help maintain replayability of a given game. And certainly No Man's Sky, which was developed here in the UK and released in 2014, is probably one of the most prominent examples of this out there. Certainly one of the most high profile cases I can think of. Now, the thing is, I've just talked an awful lot about all these different what are classical planning methodologies. They're all built around this notion of a system that is handcrafted by designers and programmers that respects logic and rules, and it knows in certain contexts when those rules will result in transitions or changes in behavior. And that's very much the kind of the classical AI approach. But nowadays, if you're talking about AI in the media, almost everyone's talking about machine learning. And it's going through this huge surge of productivity and gains in this field right now. I think courtesy of cloud computing, that has been hugely instrumental. And this isn't to say that machine learning hasn't actually been used in games. Even if you go back as far as 1996, the Creatures series was trying to use neural networks to create their characters. Black and White from 2001, that's what you see on the screen right now. The god monsters in the game, this giant gorilla monster you see here, this is actually controlled using a trained machine learning algorithm. And there was also the Total War franchise, which is still going strong to this day. The very first entries in that series used machine learning, but all of them threw it out. And a lot of it was due to the fact that the tools weren't particularly consistent, and there's a lack of accessibility and transparency. And particularly, like I said earlier, this is a very multifaceted field. So you're dealing with programmers, designers, artists, animators. And if you don't know how this character is going to behave or why it's going to do something in a certain situation, like debugging a machine learning system is much harder to do, as we'll see in a minute, than debugging a classical AI system. And so the industry has been very reluctant to embrace it. And frankly, when it comes to character behavior, we're not going to see it as pervasive as it could be in other fields. And so coming to that, when I talk about machine learning, it's worth acknowledging that machine learning is kind of a subset of artificial intelligence, and they're very distinct from one another, even though when we hear it in the media, people often think we're talking about the same thing. And what's really important to acknowledge is that, like I said, AI systems are all about encoding knowledge from an expert, a programmer or designer about the way of the world, and then a structured procedure by which we can shift from particular states of the world based on our own understanding of it. We can search for good paths through the state of all possible situations that exist in the world. Machine learning doesn't work like this. Quite often we are building a model that can process data. You're building a mathematical model, but you don't know what the mathematical model is when you start building it. And so what you're doing is you build a process where the system can learn to get better at maximizing a utility function against some training data it has. So if it was, for example, image recognition, you give it a bunch of pictures of like cats and dogs, and then you grade it on how effective it is at recognizing cats and dogs. And every time it finishes and it's not quite there, you can use the algorithm to go back and tweak the algorithm, to tweak the data structure, the computational model, until it gets to that desired output. And really the simple distinction I use for this is that AI likes to pretend to think like it's a human, because you have this expert knowledge and this notion of this is what the world looks like and how I can transition from one snapshot of the world to the other based on my own ability. Whereas machine learning pretends to learn like it's a human. In fact, a lot of machine learning is actually derived from notions of neuroscience, as well as looking at kind of human behavior. Can we reproduce this kind of phenomenon in a mathematical format? And I think one of the interesting things that's really helped spur this at the moment, or at least drive a growing enthusiasm for this, is AlphaStar. So if you're not familiar with this, Google DeepMind over the last couple of years has invested a tremendous amount of time into learning to play Blizzard's real-time strategy game, StarCraft 2. Now, this was a sort of an evolution after DeepMind was able to, they built the AlphaGo system, which was able to defeat the 9Dan professional Go player Lee Sedol. And one of the reasons for this is that the number of unique possible situations that exist in a game of Go versus StarCraft it's significantly larger in StarCraft. So if I remember right, Go has roughly 2 times 10 to the power of 170 unique possible game states. StarCraft, they haven't actually, in fact, I'm going to lift from a research paper a colleague of mine wrote. We don't know for certain, but the upper bound is 2 times 10 to the power of 1,685. So the number of states here is astronomical in the context of Go, and Go was already considered an insurmountable problem. And then within the space of a few years and a tremendous amount of money, tens of millions of dollars, in fact, Google have essentially managed to achieve grandmaster status within StarCraft. So what we're watching right now, this is actually the AlphaStar bot, and it is playing against, I'm trying to remember which of the two players it's playing against. I think it's TLO, who's a professional StarCraft player. And this was a period of which, during the development, before they released it to the wider world, that they were actually bringing in professional players to play against it so they could get an idea of its strengths and weaknesses. And the system is really interesting, and it's spurring a lot of enthusiasm for machine learning in games, but it's also not reflective of how games are developed or the ecosystem within which these games will typically find themselves in, that you could train a machine learning system to learn to play it. And the reason for that is that AlphaStar is actually trained in 2 phases. And please bear with me, I'm massively simplifying a year's worth of work here, but we're going to kind of steamroll through it. Is that it's training a deep neural network, which is the structure you see on the right-hand side. And the idea is that we're training the topology and the weighted connections within this network. These are all given numeric values, and then these are manipulated and tweaked to a point that when you feed information from the game world, the outputs which map to the game world are actually intelligent and useful. And so the first thing that they did with AlphaStar was it actually used several hundred, or was it 1,000, anonymized player data, because StarCraft has been around for a long time now. StarCraft 2 has been around for about 10 years. So they were able to pull all this player data from online matches, parse it into a format that was amenable to the system, and then train it using a supervised learning mechanism where the network was being tasked with being able to reproduce the behaviors it saw in the replays. And then once it was able to actually reproduce that behavior, it's already achieving a level of expertise that puts it past about 80% of all StarCraft players on Earth. The next phase was they then use reinforcement learning, where it would actually play against itself and other players in a league, and it would learn from its mistakes and then actually try to correct them and improve upon it. Meanwhile, there was other characters in that league who are designed to focus on their failures and actually punish them if they didn't actually learn to correct them over time. So, yep, there we go. Anonymized human data, capable of, and now it's got a 95% win rate at elite level in the game. And this means that it has an average MMR, which is the multiplayer match ranking score, of 3699, tops 84% of all human players. And we're seeing there that it's taking this raw observation data, and then that's being passed through the network. And then from that, it's then saying, okay, well, maybe we need to move a unit, or we need to train a unit, or we need to build something here, and in a way that is actually respects the game's logic, but is also makes sense in a kind of high level strategy, particularly for professional players. And so when they did it one step further, this AlphaStar League they had, where they actually had them playing against one another, with exploiters existing in the league to target particular failings that each of these characters had, they were able to reach an MMR of Grandmaster level, which means that they are in the top 2% of Europe. And in fact, they actually then let it play against people in Europe, and it was able to maintain this position. I think it's top 0.15% of all players ranked in StarCraft 2 in Europe. Interestingly, we don't know about South Korea, which is StarCraft's biggest market. And also there is a very interesting distinction between people who are good at StarCraft and then people who are good at StarCraft in South Korea, because quite often the European or American and European versus South Korean leagues, there's a huge disparity in the overall skill level. But one of the interesting things about this, one of the interesting things here is that, like I said, it's not reflective of how games are developed. They had access to the thousands of anonymized replays. They had the ability to work with the game developer who had spent years building this game up and really know the game really well. And so this was an official collaboration between DeepMind and Blizzard. But the other interesting thing is that since they were able to lift so much from human experience, it kind of bootstraps the AI to do that. And particularly, I've talked with companies who are saying, hey, can we do this for our game? Like, well, no, because you haven't built the game yet. So you don't have thousands and thousands of players who can play this game at a really high level, often at a level that exceeds the actual developer's abilities, and then be able to harvest that data for the purposes of actual research. There's also the element of cost. So this has never been made public, but even a naive calculation of the Google tensor processing units that they use estimates that I put a rough figure of somewhere between 30 to about $45 million it cost them to train it in 2 separate phases during its development over a period of 2 years. Now, I'm sure they get a discount because, it's Google, so they own their own TPUs, but it's a massive amount of expense. And for any other company, they don't really have that luxury. And particularly because $45 million is probably exceeding the budget of most video games. There's only a handful of games that really begin to break into that, exceed beyond that. And that's your Call of Duties, that's your Assassin's Creeds and games of that ilk. Like for a lot of smaller studios, you're lucky if they spend a total of a couple of $1 million on overall on a project. But what this really shows is that machine learning, and this is generally a truism of the methodology, is it's very good at identifying patterns and relations in data sets. And from that, you can begin to make intelligent decisions based on in-game behavior. And then we're actually finding really exciting ways to put this into games. And you're only going to see a couple of them here that are actually in the historic element of building better baddies. We're actually going to see a lot of really exciting innovations that are happening here that are not focused on the player, but supporting the game experience and also making lives for developers a lot easier. Oh, sorry. So the first one that immediately comes to mind, and is arguably, I would say, one of the most successful applications of machine learning in the recent years, is player modeling. And this is essentially what StarCraft was doing, what AlphaStar was doing, where we can encapsulate and capture player behavior. Because if you have the ability to capture player behavior, you can then find all sorts of interesting applications for it. Now, one area that I don't really talk about in this talk, given I was pressed for time, is, I mean, I'm not, but at the same time, you all want to log off at some point, is the notion of player analytics, the ability to recognize what players are doing in games, and then from that, making intelligent decisions about how to proceed. And particularly mobile games with their economy systems, live service or online games, such as Fortnite or League of Legends. These games are very, very focused on what players are doing at all times, because they can learn player habits, they can learn expenditure habits, they can learn social habits that exist within their games, and then they can tailor the product to suit those behaviors. But the other interesting avenue is, if you know this behavior, you can try and reproduce it. And so this is a really interesting one, is Drivatar. And so Drivatar has been in every entry of the Forza series since Forza Motorsport 5. So what we're seeing right now is I'm driving a car, and all the other cars that you currently see on the screen are AI controlled, but they all have names above them. And that's because each of these cars is actually designed to reproduce the play style of another human. In fact, half of the people that I'm racing against in this race right now are people that are actually my friends, and then the rest of them are just strangers that have been pulled in from Xbox Live. And so the way this works is it's using a process of Bayesian learning. So if you consider you can see the race ribbon and the line that's being followed along that ribbon, which is the optimal path I should be taking through this race as it happens. And you quite often see I don't follow it that accurately. I'm not very good at this game. What the system is doing is it is paying attention to what a player does at every point of a race, and it looks at how you are driving your car along that part of the race ribbon, across every bend, across every straight. How close are you to the line? How much are you gunning the vehicle? Are you in control of the vehicle? And it generalizes this so that it can calculate at any point in time. So it uses a neural network and it trains it through this Bayesian learning process to say, at any point in any race, in any vehicle, what would Tommy do? And it calculates the expected utility of the vehicle. So there is actually an underlying AI controller that's running underneath all the other racers, but it says, okay, here's the optimal path. How closely will Tommy follow that optimal path? And it actually works markedly well. So they take all this data and it's pushed up into a server in the Azure cloud, and it trains it all online. And one of the great things about this is that once it's trained, the inferencing is super fast. It doesn't take any real processing time to actually ask it on any given frame of the game, what should this character do? It's often much, much cheaper than using a pure rote logic system. And the really cool thing about it is that it means you can appear in a race, driving a car you've never driven before, on a racetrack you've never driven before, in a friend's game, but you also might appear in a new release of Forza that you've never played, because it uses the same data and it can apply it to different games. So there's this really interesting thing where I actually see my cousin a lot. This is Forza Horizon 3. I keep seeing my cousin playing this. I know she's never played Forza Horizon 3, but she keeps coming and ruining my races. And another really exciting one that came out of Microsoft is Shadow Mode in Killer Instinct. So this evil dude with the kind of purpley haze, this is a shadow of Jago. Now, on the left-hand side, I am Jago. And on the right-hand side, I am also Jago. This is a shadow. This is an AI character that is reproducing me. So I have actually trained this fighter to play like I do. And this uses a procedure known as case-based reasoning, where what it does is at every point in the game, in the context of a fighting simulation, it looks to see what I do in this situation. Do I try and execute a combo like this? Do I back off and then start throwing fireballs, which is actually a tactic in fighting games known as zoning? And so what it does is it tries to then really fine-tune this for every possible situation. Am I going to attack? Am I going to defend? Am I going to try and pull off a combo? Am I going to block? And so now I'm actually in this weird zoning battle against my own AI because we're both doing the same thing. So I want to bear with this for a second because it actually catches me out a couple of times, which is really interesting. And the tactic of jumping over and throwing you, oh, hang on, I just beat it and I taunt at it. This is something optional. I don't have to do this, but I like to taunt it because I just defeated it. And then, like I said, this is actually, like I said, it's reproducing all these different things at different time points. So it can reproduce combos like this here, but also it's going to actually beat me if I remember right in a second. It figures out what I'm going to do, and then it taunts because that's what I do. And so this is an interesting procedure because the game is, again, monitoring what I'm doing at all times, but it will actively update the shadow fighter if I wish. So I can have a really good game and then say afterwards, oh, right, that was a great time. I did really well against this other player. And then the game will give me the option to say, do you want to update the shadow to take on this new information? So your AI version is like your best self. And I think sadly, they didn't lean into it as much as I think they should have, because I think one of the greatest opportunities here is particularly with the rise of professional gaming, and fighting games are a very competitive esports arena. In fact, fighting games were doing esports before it was called esports. There's an interesting opportunity to then let regular players like me have a chance to play off against high-ranking professional players, and because the shadow can reproduce their behavior. So, like I said, Drivatar for a long time was one of the few examples of modern machine learning for character control, but it was an innovation prior to the current kind of deep learning boom. In fact, it was actually a research project for many years at Microsoft Research in Cambridge. More recently, with the rise of deep learning, we're beginning to see actual valid applications for AI character control of machine learning in games. And the very prominent example was from last year by MotoGP. And developed by Milestone. And this is a neural network player called Anna. So every other racer that you currently see here has been trained using deep learning. Now, one of the reasons that this works really well, so this has no human input, no human insight. They didn't rely on player data here. They just let the racers go on the track and learn how to drive. Now, one of the reasons that this is probably, I would say, one of the best applications for machine learning in the context of games is this is a real-time continuous control problem. You're dealing with a vehicle that is moving through simulated physics. It has to respect all these different forces that are being applied to the bike, whether it is the surface of the road, whether it's the engine torque, whether it's, and how aggressively I'm steering. And these are things that this kind of continuous control is something that, like I said earlier, machine learning is very good at catching patterns. So this is a great opportunity for it to kind of really maximize this. And as you can see, I'm terrible at this game. I really struggled. Like, I played this game for about 45 minutes to get enough footage that I could show it in a couple of videos and in this talk. And these are the easy AI characters, and they're already just driving circles around me. It's ridiculous. But one of the really interesting applications outside of character control is actually in animation. And as any animator will tell you, building the animations is the easy part. The hard part is figuring out how animations blend together. And so what you want is to find, and games will have, all games have animation controllers where a character, if they're moving through the space, will know how to change. So for example, if the character goes from an idle standing position to walking and then running, there will be specific points in the animation controller that says when the speed of the character is at this point and this value is at this threshold, we transition, we blend from one animation to another. This is a massive time sink. It's also very difficult to get right. And one of the bigger problems is also the notion of foot sliding, where a character looks like they're running, but also like sliding on the floor as they do it. And so this is actually some really exciting research here that's coming out of McGill University in collaboration with Ubisoft, where they're working on a procedure known as motion matching. And so this is a reinforcement learning algorithm that learns the optimal blend points between animations. And this was actually a project that started out outside of Ubisoft. And originally it was used in the Hitman series, so Hitman Absolution, and then the 2016 reboot of the Hitman series, hence the slide earlier, used this procedure of just giving the machine learning system the animations and then figuring out the points of minimal difference between between two animations. But also the new thing that they're working on, so the developers who worked on it on Hitman moved to Ubisoft, and it's since been used in For Honor and Assassin's Creed and a few other games. But the thing they're really focusing on now is the physical properties of the environment. And so you can see here, this character is really reacting to the local space and figuring out how to step up or step off of all this really rocky and awkward geometry in a way that a human designer would have a huge amount of effort trying to cater to all these different situations. And odds are they would still have massive gaps if this was developed by hand. But here it is, all running within a machine learning system. And again, it's a very fast system to actually run during playtime. Conscious of time, but we've only got a couple more here I think I wanted to talk about. Very briefly, talk about cheat and exploit detection. So this is something I don't have any public things to show, but I know that this has been developed. Counter-Strike Go, or CSGO, developed by Valve, which is a popular first-person shooter. They've been slowly implementing deep learning, or deep learning neural networks, where what they're doing is they're using it to detect bad behavior or undesirable or strange behavior when people play the game online. And one of the reasons for this is that games such as this have an awful lot of issues with assist bots or wall hacks, where people use third-party software that kind of injects into the game to allow them to have a competitive advantage. And so these systems have been very good at being able to avoid being detected by the developers of the game. And so they started using this VACnet, which is a system that is able to monitor their behavior in the game and then say, okay, we think that person was cheating. And then what it does is it actually goes through a procedure of a separate system called Overwatch, no relation to the game Overwatch, where it reports it to a human moderator for the company, who then go and have a look at the data. And they actually watch the replays to see whether or not they can actually ascertain it was, in fact, someone was cheating. And the system has achieved 80% accuracy in submitting valid cheat reports, which is interesting because this is, in comparison, the average human's success rate at identifying a cheating player is only 30%. Level generation, this is a huge thing that's happening in a number of places, but notably King, who are the creators of Candy Crush, they are deeply invested right now in deep learning for not just automated playtesters, but also tools to support level designers and even entire level generation systems. And this is because, Candy Crush needs to have more content. You need to have more levels for people to play. And it's a really difficult problem to ensure you have continued diversity in the levels that are being generated, and also ensuring that they're going to be interesting or fun. And so I know that this is something they've been actively pursuing now for about 3-4 years, and they haven't rolled it out entirely into production, but it's slowly creeping out into their actual product. One of the last ones, I like this one as well because it's got some fun videos, is physics approximation. So we talked a little bit about computational load and how expensive it can be to run certain processes in a game. AI is always going to be a difficult one. Physics is a very demanding one. So physics systems in games are often very, very demanding, particularly as the scale of the game increases. This can be in respect to both rigid body and soft body physics, but there's often ways to creatively work around it. And a really good example of this is the image here. You can see this is art from Rainbow Six Siege, which is a popular online shooter where you're able to destroy and damage an awful lot of the environment. This is because you're meant to be like a tactical counterterrorism unit who are breaching into an environment to rescue hostages. Now, one of the things they do here is that they often pre-compute physics damage before it happens. So in the context here of my character going with a sledgehammer, at the point that I go to raise the sledgehammer, it knows roughly where I'm going to actually hit the wall. And then from that, it pre-computes the damage, figures it out, and at the point of contact, it then essentially removes the existing wall and swaps it out with the wall that's actually been damaged by the perceived physics. And then the hard part of that is that this is an online game. So it happens on my machine, and then it has to pump up to the server, and then it has to share all that information across all the other players. And so this has a huge computational load that they really have to try and optimize, and they cut so many corners where it actually means that I get to see the physics damage I did for about a quarter to a half a second before everybody else does. And they minimize this as much as possible. But here's some bunnies. The other thing that's really cool about this is that this entire simulation, which has over 100 bunnies, I think, is only using up about 2 megabytes of memory in the graphics card. That's insane. This is also research coming out of McGill University in collaboration with Ubisoft. And one of the things that they're doing is that they're taking existing physics systems that have been written and coded in a traditional physics engine, and then giving it to a reinforcement learning algorithm to say, can you learn the physics phenomena that's happening here? And if you can learn it sufficiently, can you then reproduce it? So they take these existing pre-written, coded up physics simulations, and then once it's trained it, the knock-on effect of this is that, like I said, physics code is really expensive. But if you can get the reinforcement learning system to figure it out, the inferencing time and inferencing load is incredibly short. And so this is currently running at nearly 3,000 frames per second. The average video game, you're lucky if it runs 30 to 60 frames per second. And so this is only using up 8 megabytes of memory in the graphics card. And it's achieving this really high level of fidelity in this physics simulation. And it's absolutely insane because also once they've reproduced it for one type of physics phenomena, you don't have to duplicate the physics engine for it. You've already got it in memory. Hence all those bunnies were using the same inferencing engine. And all of these gentlemen here with cloaks on are all using the same inferencing engine. So it's only using up 8 megabyte of memory in the graphics card. So the last one, there's a whole bunch of other stuff, was texture upscaling. Apologies for the slightly gory graphic. This is a really interesting work that's not happening so much in the games industry yet. It's happened a couple of times, but it's actually becoming very big in modding communities. So the idea is that you can achieve what's called super resolution. You train a convolutional neural network such that it can learn to produce higher resolution versions of lower resolution images. And so what people are doing is taking really old games, such as Doom. And so this is actually footage recorded from a computer that actually would have played Doom when it came out. This is an Intel 8486. I actually owned one of these when they came out in the early 90s. Yep, I'm old. And this is it playing the original Doom. And the interesting thing here is, yes, the resolution isn't great, but also the texture quality is very muddy, it's very blurry. And so what people are doing is going through this process of saying, right, well, what if I can just feed these textures into a super resolution system and then play it again at a higher fidelity? So this is Doom being ran on, I think it's GZ Doom, which is one of the modern Doom mod platforms. So you can see it's running at a higher resolution, but also they've passed all the textures through the upscaler. So the super resolution system, I think it's called, was it Doom Upscale 2X? So this was something that actually a team of modders went away and developed, and they trained the system against gaming textures. So it could learn how to upscale these game textures to higher resolution. And then they just threw every texture from Doom into it. And then they use those textures in the final game. And so there's an interesting push-pull here because some of it looks much higher and much crisper, I think. And one of the really interesting things about super resolution is it's having to fix or fill data in the middle that, that isn't really in the original image. And so sometimes this works really well and sometimes it doesn't. And Doom isn't the only case that this is happening in. I know that there was a fan community based around Final Fantasy VII, the original version of it, not the recent remake, where they're passing in so Final Fantasy VII, all the background art is entirely textures. So they're feeding all of it into these systems to see if they can then reproduce the entire game. And I think the thing is that one, training these networks is actually really difficult to get the quality that you want. And two, there's a huge number of textures that they need to upscale. So it's a very long and gradual process that they're going through. And so this was just a very high level overview of some of the interesting opportunities there are. But just to quickly mention some other ones that I didn't really talk about, you've got real-time text analysis. This is something that's now happening in game platforms, notably the Xbox ecosystem now actually pays attention to text interactions in gameplay, and it will flag them for toxicity and undesirable behavior. And I know that they're interested in looking at this for voice related in-game stuff as well. Automated testing. So can we actually deploy AI systems, be they classical or machine learning, to find bugs in games before it happens? This is already something that's used quite pervasively in a number of situations using classical AI. I know the Division 2 uses this to great effect, and Electronic Arts has been investing in machine learning bots to learn to find all the bugs in their Battlefield games. Voice modulation and reduction. So something like Zoom or Teams or Discord is often using voice modulation or reduction to kind of tighten it up and make sure that this sounds really crisp and really clear as we're chatting to one another online. And of course, there's also things like analytics, deep learning super sampling, which is now becoming part of modern graphics cards to replace existing anti-aliasing technology. And I think there's a few other things that I can't remember. But yeah, we've already got far enough into this presentation. And so this has been something of a whirlwind, I will concede. But I hope you found it interesting. And it's sort of this really interesting space we're in right now where games are changing quite drastically to the point that machine learning is having a huge impact on how we make games, but not necessarily on what the player experiences. And I think that's going to continue to grow over time. But I think there's still a lot of opportunity for growth to find ways to apply machine learning for character behavior and what have you, in ways that are more supportive and more amenable to the creative process and kind of helping developers and designers. But I guess time will tell, I guess. Yes, sorry, I think that's it. Thank you very much for listening. I hope you've enjoyed it.
That was brilliant, Tommy. Thank you so much for this presentation. Super interesting. Massively new to me. I've got a confession. I have never played a video game.
Oh, wow.
Don't know if it's my age or what, but yeah. Yeah, it was a really interesting talk. I found it super interesting that the sort of beginning of the talk, when you're talking about it being creative and having to be creative, because I think often science and creativity are kind of meant to be split, but I think they're absolutely like linked together. So I found that really interesting. I think the chat is open. So if anybody has any questions, please just type it in the chat. Or if you raise your hand, and I think you can unmute yourself as well. I think I turned the chat off earlier, so is the chat working? Miranda, can you check?
I have a question.
So Tommy,
Okay.
I've got a question if I can.
Yep, fire away.
So you've said that machine learning is growing in terms of more modern games, but so is players' expectations in terms of what they get out of the game, particularly in terms of perhaps like the realism and complexity of AI players, particularly as sort of graphics within games are starting to reach a bit of a plateau in terms of, sort of continual development. So I was wondering whether you think there's scope for genetic algorithms to be applied to machine learning and neural networks to increase that sort of sophistication, but also human randomness and realness that's what we really want to see in games, if that's not already happening.
So it's so interestingly, like my PhD, part of my PhD was applying machine learning to non-player characters in games. And it's interesting how I was originally a huge advocate for the idea. and then kind of went backwards from it over time. The more I actually got to meet and actually engage with game developers, and became a game developer myself, you're like, oh God, this isn't actually that fruitful. And certainly coming back to the idea of the notion of accountability, that was quite often historically the reason why nobody wanted to use it. And I have actually been involved in a couple of knowledge exchange programs with studios many years ago during my PhD, where we were looking at neural networks and saying, hey, we could actually use this for characters. And they actually ran some experiments. And one of the reasons they really didn't like it was if something went wrong, they couldn't figure out why. Or if their QA team reported something, they couldn't go back in the code and begin to actually ascertain or debug why that was. Now, I think that's changing to some extent. I think that is improving. I think we're going to see some really interesting growth in the next 2, maybe 3 years. Because one of the things that's happening now is instead of going through this sort of arduous process of building characters from scratch. And one of the biggest problems I think the games industry suffers from is that it has to reinvent the wheel all the time. Technology doesn't really adapt from one engine to another. And so even if you have, so for example, if Ubisoft make Assassin's Creed, they make Far Cry, they make Watch Dogs, they make Rainbow Six, they make whatever, hardly any of them are in the same engine. So the Division's built in a different engine from Far Cry. Far Cry's built in a different engine from Assassin's Creed. Assassin's Creed is built in a different engine from Rainbow Six. So anytime they have an innovation in one of them, they can't translate it to the other one without a huge amount of engineering workload. And so I think being able to find a way for machine learning that has some generalized intelligence in some context that's pre-trained could then be dropped into these different situations and then parameterized such that it could work well in that space. That would be really cool. And I know that Electronic Arts in particular are really invested in imitation learning. So something they're really aggressively pursuing is, could we actually just get our designers to sit and play the game the way that they want the characters to behave, and then the AI can reproduce it? And so the great thing about doing all this outside of the game is that once it's pre-trained, you can then, and it's also, this is the reason why Forza does everything in the cloud, is training these systems on the host device is too much work. It's massive computational burden. Even now with the new consoles, you're not going to get the amount of CPU budget and resource to actually run this. So they're going to offload that somewhere else. But the really cool thing is that then when you get it in, when you get the trained neural net or whatever it is back in, like I said, inferencing time is super, super, super fast. And this is why, so you have Intel's been rolling out their new chipsets recently. AMD's rolling out new chipsets. Well, what was it? Apple just announced their M1 processor in the last week, which is designed to optimize AI. And what it really is just a chipset that maximizes matrix math, because that's what the majority of machine learning is just matrix mathematics. So I think there's a really interesting opportunity for them to start really injecting this into the games, because I think they're more confident that it can work. And if it doesn't work, they can actually isolate why and fix it. But I still think it's interesting in a cost level. Again, I think when I was talking about DeepMind and AlphaStar, like the amount of money they're having to spend on just training these systems, it's very different to train a system that becomes the most godlike, perfect player of StarCraft in the universe versus a character that is good to shoot at you in Far Cry, for example. But I think there's still scope for that to eventually come around. Not sure if that answered the question.
Yeah, no, I think I think it did. Thank you.
Hi, Tommy. I have a question.
Sure.
My question is 2 parts. Thanks for the great presentation. The first one is, you mentioned that for machine learning, you mentioned that it's often not suitable for the development process. But I'm thinking that you used your AlphaStar example, and you had in that example a lot of computational power, sure, but you also had a lot of data and priority experience replay. But wouldn't a live service model, like we see in a lot of MOBA games, be ideal for this kind of a challenge? Because essentially you have unlimited amounts of data because people are playing all the time over long periods of time of various levels. And hence you'd be able to create a reinforcement learning model with that data.
Yes.
And then if you don't mind, the second part is, I'm glad that you mentioned the transfer learning thing. I'm in full agreement. I think just like back before ImageNet was rolling out the classification models, everybody had to train everything from scratch. So wouldn't it be possible? And there have been some papers to show that it works in Atari, that models trained for, let's say, one Atari game perform well jump-started on another model, on another game, provided they're doing a similar task. So
yeah.
What do you foresee for that? Thank you.
Yeah, so regards the first part, you'll notice that the games that have achieved the most prominence in sort of big AI companies solving them are all live service games. So you had StarCraft, you have things like Dota 2. These are games that record all player data, that have millions of people that play them, that have masses of archival data of millions and millions of games that have been played all around the world. And certainly, I briefly mentioned the situation with King, and I know that the what's the other company called? I forget. People that make Clash of Clans, I forget their name. I know that there's something that they're really interested in, because one of the things, they are building automated players, and they're building automated players from watching how people solve puzzles. One of the things they're interested in is, can we categorize or create profiles or personalities of players so that you can see how well a different type of player might respond to a certain game or not. And I think it's fair to say, I didn't really get to talk about this in the talk, but when I talked about player analytics and the ability to harness player data, either to reproduce it or model it or what have you, every major game company has an analytics team. Electronic Arts has a massive analytics source. Ubisoft has a couple, I believe. Square Enix, every major mobile gaming company has one. And this is actually really interesting, because 10 years ago, the field didn't exist. In fact, one of the most seminal publications was actually made by a colleague of mine, Yergos Sinakakis, and Julian Degelius, who are based at the University of Malta and New York University, respectively. This project was on exploring player behavior in Tomb Raider, and this was a collaboration with the studio. In fact, I made a YouTube video about this, if you're interested in finding out more. It was the first time anyone actually realized, hey, if you actually pump this data into a machine learning system, we can learn something about the players. And then what they did was they actually were able to infer how well the player would actually get on playing Tomb Raider, as well as they were able to do some really simple and supervised learning and actually cluster players based on certain traits or profiles. The second topic, coming back to, because it was transfer learning. I think one of the things that Electronic Arts in particular are really interested in is they're a company that really like making shooters. You know, they have Medal of Honor, they have Battlefield, they have Titanfall, they have Apex Legends. So they really love making shooter games. And so can you reach a point that you can train bots that are very good at shooter games? And then, or at least a certain threshold of the skill or ability required in each of them, in terms of just general coordination and moving around the space, picking out targets, hunting them down, eliminating them, and then using that as the bootstrapping mechanism. So like we talked there with AlphaStar, the idea that they were bootstrapping from the human playthrough, and then they used reinforcement learning through self-play to specialize. What if you could then take that boilerplate trained player and then build on top of that for a Titanfall character or a Battlefield character? I think that's one of the really interesting avenues they could go with there. They've been very quiet recently, which makes me think they're going to have something to say next year at GDC, which now that I'm involved in organizing it, I'm going to see if I can find out. But yeah, I think that's a really exciting opportunity, either as playtesting or as actual in-game characters for people to play against.
Thank you. Thank you. Looking forward to hear your scoops. And I've been a fan of YouTube channel for a while now. I didn't know it was you coming to talk, actually, because I'm so familiar with your YouTube channel name. So yeah, excellent.
You hear the voice and then go, hang on a minute. Oh, I noticed there's a question in the chat from Susan. Thank you so much for such an interesting presentation. You're very welcome. Have you found that people are grumpy following a game? As in, just to clarify, is this as in they've had a negative experience during a game and then they feel grumpy afterwards? Or is it in the context of following? Okay, so they feel grumpy. Yeah, I mean, I can speak from experience. I feel quite grumpy sometimes. One of the really interesting things I know a couple of my friends have worked in analytics for games companies is being able to capture negative experience and been able to conceptualize why that they've had a bad experience, because an awful lot, because of course video games are a form of relief, a form of stress relief. In fact, what was it? Everybody in the press was getting all excited because the Oxford study from a couple of weeks ago that said, hey, look, games are a great way, a social mechanism to make yourself relax, which everybody who's been playing video games for the last forever already knew. But when things go wrong, you're not entirely sure whether it's the game that's at fault or it's maybe they've had a bad day. Maybe they're just not, they've had a really tough day at work. They sit down to go and play a game that, right, you'll never meet them. It's fine. One of my friends who I make games with has a very bad habit of getting into a very bad mood when he's had a bad day. He plays online shooter games. He likes to play things like Call of Duty. But the thing is, when he then has a bad game in Call of Duty, he blames the game. This man has designed several games. He's developed several games. He knows what he's doing, but at the same time still projects onto the game. And I think there's a really interesting space there for AI to capture this, because this is a very qualitative metric you're trying to gather. How much fun are you having? How much of a negative experience are you having? But even as someone myself who's developed games, one of the things that I found immensely valuable is when I make a game, and I've made a couple of games that I've taken out on events, and you tour around the UK, obviously not right now, but you sit and you put it at a trade show. So EGX, for example, if people are familiar with that, I've shown games at EGX. You stand 10 feet away, completely distance yourself from the player and let them just play the game themselves, and you just watch. You can see interesting behavioral quirks. You begin to see their body language change. You get to see how serious their face is. Are they happy? Are they smiling? Are they frustrated, but they're still holding onto the controller really tightly because they're enthusiastic? And you can learn so much about why people get upset about a game, because sometimes the problem is they're having a bad day. Sometimes is the game, they're having a bad experience, which maybe you can try and account for, but sometimes it's also you've built something in the game that they can't even explicitly quantify. But if you see it enough times, you begin to learn from it and go, oh, this needs fixed. And then you fix it. And quite often at events, you fix it in the hotel that night, patch the game, put it out tomorrow morning, and then wait and see what people's faces are like the following day. It's a very risky. I think the record we had was we patched a game 12 times in 4 days, and I'm never doing that again.
Well, thanks. So I think that we've not got any more questions. Thanks for answering all those questions. I'm going to pass on to Chiara so we can go into some breakout rooms, and if there's more questions for Tommy, you can ask them there. Thank you, Chiara.